Have you ever heard of the Santa Clara Valley? In the late 1960s, it was just a dusty part of Northern Californian basin in the US. Not much going on other than cacti and coyotes. By the early 1970s, building in the desert began as high-tech industries had started to relocate to this cheap land. The area is now home to the world's largest technology companies, thousands of tech startups, and about 250,000 IT workers. These days, Santa Clara Valley is better known as Silicon Valley, and we've all heard of that, right? The whole industry is based upon the production and use of semiconductors, the innovation at the heart of the technological revolution. The physics of the semiconductor is pretty simple, so let's take a look. This is Think 4. We imagine the electrons of an atom in orbit, or maybe in shells around the nucleus. And this is a great start to understanding how electrical conductivity works. The further from the nucleus the electrons are, the more likely they are to move around and carry electrical energy with them. When we have a collection of atoms bonded together in a solid, these electron orbits, which are split into levels, becoming larger bands, as the electrons from neighboring atoms occupy similar areas, but not exactly the same space. The outermost energy bands are the important ones. These are called the valence band and the conduction band. The conduction band is the furthest from the nucleus and is not completely full, which allows the electrons to move and conduct. The valence band is one step closer to the nucleus and is always full of electrons. As a result, the electrons are not able to move. The space between these two bands is called the band gap. In insulators, this gap is so big that there is no chance of electrons moving between the conduction and valence band. In conductors, these two bands overlap to allow electrons to move freely and therefore conduct electricity. Finally, in semiconductors, there is a small band gap which electrons can overcome if we give them a nudge. This is crucial. This means that their materials can either be conductors or insulators under different circumstances. They can be molecular-sized on and off switches. The way to create the best semiconductors is actually to cheat by using doping. We take a semiconductor material like germanium, which has 4 outer electrons, and add a small amount of arsenic, which has 5 outer electrons. This means there are some extra electrons free to carry charge in our doped semiconductor. Because we have extra electrons, we have an overall negative charge, so we call this an N-type semiconductor, N for negative. Alternatively, we can add an atom like indium with only 3 outer electrons. This creates a hole where there is no electron. This acts like a positive charge, as to fill the hole, we must remove an electron from somewhere else, reducing the amount of negative charge in the material. We call these P-type semiconductors as they move positive charge in the form of a hole. The semiconductor changed everything. They are, and will be for the foreseeable future, the main component of the vast majority of electrical systems in the world. Everything uses them, from your phone, your drone, and your laptop, to operating theaters and power stations. They changed the Santa Clara Valley in ways that very few people had foreseen, and in doing so, changed all our lives forever. This was Think 4. Thanks for watching.